So what I was just saying there at the end of the first video is notice that the distance between the bag and the helicopter hasn't changed, because with respect to each other, they're still doing the same thing, right? The helicopter is just horizontal and not falling or rising in the first one, just the bag is falling. But in the second one, they were both rising at the same rate. So with respect to the helicopter, the bag is just falling. And in the third one, they're both descending at the same rate. And so again, with respect to begin with. And so again, with respect to the helicopter, the bag is just falling. So the distance between them in the end stays the same. All right, let's move to number 11. A weather balloon is floating at a constant height, which means VI is going to be 0 when it releases a pack of instruments. So VI is 0. A should be 9.81 meters per second squared down. If the pack hits the ground with a velocity, so it's telling us our VF, and it says negative 73.5 meters per second, and of course that negative means it's going down. How far does the pack fall and how long? So part A, we want delta D. I have a VI, an A, a VF. I need a delta D. I'm going to use our equation. VF squared is equal to VI squared plus 2A delta D, and I need to rearrange for delta D. VI goes to 0, divide both sides by 2A. So VF squared over 2A. Everything's going down, so I can call down positive. So it'll be 73.5 meters per second squared over 2 times 9.81 meters per second squared. If you want it, you could have called down negative and then just put them both in as negative. So 73.5 squared and then divide it by 19.62, and you should get 27.344. So delta T is equal to 27.344 meters. Works out to be positive, but I called down positive, so this will be down. Part B wants to know how long does the pack fall. Easiest way to find the time would be with A. A is equal to VF minus VI over delta T. So delta T is equal to VF minus VI over A. VI is 0, so delta T will be 73.5 meters per second divided by 9.81 meters per second squared. Again, if you wanted to call down negative, both of those would be negative, so it would still work out to be positive, and you're going to end up with 7.49, is it 24 maybe, seconds. Okay? Number 11. Number 12 says, a tennis ball dropped from 1.2 meters above the ground. So delta D is 1.2 meters, and it's going to be going down. It's dropped, so VI is 0. It's falling, so A is 9.81 meters per second squared, and it's also down. It rebounds, so there's a second part here. Delta D2, it rebounds to a height of 1 meter. Okay, with what velocity does it hit the ground for part A? So we want to find our VF. So A is equal to VF minus VI over delta T. The VI is 0, so VF is equal to A delta T. So VF, oh, I don't use that one, I don't have time. Sorry about that. How about using, what did it ask for? What velocity does it hit the ground? So use VF squared is equal to VI squared plus 2A delta D, no VI. VF squared is equal to 2 times 9.81 meters per second squared times 1.2 meters. Again, I'm calling down positive because everything is going down. So we have 19.62 0.62 times 1.2, and you get 20, oh, that's VF squared. Take the square root, and you get 4.8522. 4.8522 meters per second. And again, that will be down. Part B, what velocity does it leave the ground? With what velocity does it leave the ground? So over here, so this is when the ball was going down. Here, the ball's going up. And it's going to go up until it stops. So the VF is going to be 0. The A is going to be 9.81 meters per second squared. This will be down. This one's up. And this time we're looking for VI. So you want exactly the same equation, but this time you're going to solve for VI. So VF squared equals VI squared plus 2A delta D. The VF is 0, and it'll be VI is equal to negative 2A delta D. So VI squared is equal to negative 2. My gravity has to go in as a negative this time because it's going down while the ball is going up. And so VI squared is going to be 19.62 meters squared per second squared. Take the square root of, take the square root of 19.62 and get 4.429 meters per second. That will be up. Part C wants to know, with the tennis ball is in contact with the ground for 0.01 of a second. So delta t is 0.01 of a second. What will be the acceleration? So now you have to think about it's striking the ground with a velocity of that 4.8522 meters per second, and it's leaving the ground with a velocity of 4.429 meters per second. So this becomes my new VI, and this becomes my new VF, and I'm given a time, and it wants A. And so I can just use A is equal to VF minus VI over delta t. My VF is upward, goes in as a positive, 4.429 meters per second. My VI is going downward, so it goes in as a negative, 4.8522 meters per second. And my time is 0.01 of a second. This minus a minus ends up being a plus. And then divide by the 0.01, and you should get an acceleration of 9.28166, if you don't round at all, meters per second squared. Oh, I might have put my decimal in the wrong spot, though. It should be there. 928.166 meters per second squared. Works out to be positive, which is up. I mean, that should make sense. The ball was going down, and then it just got turned around, and now it's going up. So the acceleration must be upward. 928. That's a big acceleration. All right, now let's switch pages to the back side of the FreeFall sheet. And I asked you to do numbers 6 to 9. All right, number 6. While driving from Fredericton to Moncton, one morning your physics teacher gets stuck behind a slow driver going 27 meters per second. So VI, 27 meters per second. Finally hits the gas with a constant acceleration. A is equal to 1.864 meters per second squared. Accelerates for a distance of 190.90 meters. What is the VF? Completely straightforward. VF squared is equal to VI squared plus 2A delta D. VF squared is equal to 27 meters per second squared. 2 times 1.864 meters per second squared times 190 off the screen. 0.9 meters Do the math. Don't forget to take the square root.